This is section 5.2. We're talking about partial variation. Michael.
Earth is made up of several distinct layers. Beneath the oceans, the outermost layer or crust is 5 kilometers to 12 kilometers thick. Below the contents, Earth's crust is 25 kilometers to 90 kilometers thick. The mantle is about 2,750 kilometers thick. The outer core is about 2,260 kilometers thick, while the inner core has a thickness of about 1,220 kilometers. Deeper layers are hotter and denser because the temperature and pressure inside Earth increase with depth.
Good. Everybody know that about the Earth? The further you go down, the hotter it gets. Temperatures at the core of the Earth, they approach this temperatures on the sun, on the surface of the sun. Okay, it gets actually that hot. The investigate says, what is the relationship between temperature and depth? The temperature of Earth's crust increases by about 145 for every kilometer below the oceans. The temperature increases by about 21.75 for every kilometer below the continents. Starting at a temperature of 10 at the surface of Earth's crust, make a table showing the depth and temperature of Earth's crust under the ocean and under the continent at depths between 0 and 5 kilometers. All right, so our first point will have a depth of 0. What's going to be temperature under the ocean at a depth of 0? Who can tell me? Okay, let's go up here. Anybody? So we're starting at a temperature of 10 at the surface of Earth's crust. So, Adam? 10. Yeah, 10. We're going to start at 10, right? And for under the continents? 10, right? That's our starting point. Between 0 and 5. So our next depth, we might say 2 point, or let's say 2. So at a depth of 2 kilometers under the ocean, what's going to be our temperature? Besides Adam, anyone else? Under the oceans? Tim? 155. Okay, and that's because we know it goes 145 for every kilometer below the ocean. Sorry, but we've gone 2 kilometers, so we should have went 290 plus 10. So this would be 300, right? Yeah. Okay, and under the continent, Tyler? 31.75 degrees. Again, we went 2 kilometers. Adam?
53.5.
Because I chose to go a depth of 2 kilometers, you have to double these values. Okay, you might have went 0, 1, 2, 3, 4, 5. Okay, and then they would have went up by those respective amounts. Okay, let's say 4 now. Yeah, Hugo.
590.
Thanks. Okay, we're gonna go another 290. So 290 plus 300 is 590. And then finally this one. Yeah, Tyler?
97 degrees.
Sounds right. Okay, so if we were then to plot this, which one first is our independent and what's our dependent? Sal?
The independent would be the depth in kilometers, and then the independent would be the temperature.
Good. Again, because we're choosing the depth to go to, and then we're measuring the temperature. Good. So we have 1, 2, 3, 4, 5, 6. And temperature goes up to 590. Oh, let's put 600 up here, 300 there, 150. So our first point is 0, 10, and 10. So there is our first point. Second point is at 2, 300. And our third point is at 4 and 590. So there's one line. Our second graph is at 10 and 10, so the same point. 2 and 53, so 2 and 53. And then 4 and 100. So there's our second line. Okay, so we have two very distinct lines. Both of them do not start at 0, 0. So because of that, this is referred to as partial variation. What's the difference between partial variation and direct variation? Mark.
Direct variation has to start at the origin.
Good, yeah. Direct variation always starts at 0, 0. Okay, partial variation does not. Okay, so when the independent value is 0, the dependent value is not 0. Okay, for partial variation. Okay, so we plotted a temperature versus depth. On the same grid, plot temperature versus depth for data under the continents. So this one is oceans. And this one here is continents. Right, how do these graphs differ from those you made for direct variation? We just talked about it. Nicholas, how do they differ again?
Direct variation starts at 0, 0 on the graph.
Excellent. Whereas partial variation does not. All right, number 5. Consider the equation T equals 145D plus 10, where T represents the temperature in degrees Celsius under the oceans and D represents the depth in kilometers. A. Substitute D equals 1 and calculate T. Repeat for 2, 3, 4, 5. Compare the results with those you obtained in step 1. All right, so we're going to substitute in D here for 1. So we're going to get T is equal to 145 times 1 plus 10. So we get 155. T2 equal to 145 times 2 plus 10 is equal to 300, etc. So how do these results compare with these results in the table? Christian at the back, how do they compare? So when I had a depth of 2, I got a temperature under the oceans of 300. When I have a depth of 2 subbed in for D here, I got a temperature of 300. So how do they compare?
They're the same.
They're the same, right? So then, would you agree then, Christian, that this equation works well with the graph that we created on the previous page, right?
Yes, for depth on the ocean.
Excellent, good. So explain why the equation works. Can you explain it? Max.
Because it already includes the plus 10. Right?
Excellent. So the reason why it works is because the 10 is the initial value of the Earth's temperature. So that has to be, we have to add that 10. And that's the reason why it works. When D is 0, our value for our temperature is 10. Okay, Adam?
If it's the initial and it starts at that, wouldn't it be, why wouldn't you have it 10 plus 145D?
Doesn't matter. They're the same thing. They're the exact same thing. It's like 4 plus 5 and 5 plus 4. They're both 9, right? Doesn't matter the order. Yeah, Tyler.
So another question like them to create this formula, I was asking, so like they kind of looked at it and looked at it like if they wanted to make it start from 0 to make them direct variations and then find the difference between each information and just add it.
Sorry, was that a question you were asking?
No, I was asking no, what's the question? I was asking, did you do that to create the formula? Or do you use it for the
Ask me again, sorry, I missed the question
So
here.
I was looking at the chart, right? And the 145D is just the chart as if they were to all start from 0, which is a direct variation. And then they looked at the information within the column and see that it difference of 10, so we just add 10.
You could do it that way, but I wouldn't suggest that. No, I'd say that that's more complicated than just realizing that initially when the depth is 0, your value is 10, and then go from there. Okay? You'll see, as you do more examples, you'll see how it works out. Justin?
So if it's when we're doing a chart, or we're doing a graph of partial variation, and it doesn't start at 0, we just add where it starts from at the end of the equation.
Yes. Okay, so explain why it works. We did that. Write a similar equation relating the temperature under the continents with depth. Nicholas. So we have to write an equation like this up here, but for under the continents. Remember, in the continents it said the temperature increases by about 2175 for every kilometer below the continent. So what would the equation be? Temperature equals
Whichever it is, like on the ocean or crust, so I don't know which one. Okay,
under the continents.
So 21.75 K, I guess.
Not K, but
K.
the depth, D, right? Plus what?
No.
What's the initial temperature at 0 depth?
It's 0.
No. Michael?
10.
10, yeah, it's the same, right? Okay, so there's our equation. Any questions, guys, how we came up with that? All right, let's describe the parts of the equation and how they relate to the data in your table and graph. All right. So parts of the equation, mainly I'm looking at this part and this part. How do they relate to the graph? Let's describe them. First of all, what's that first part? The 2175. Henry.
It's like the increase in temperature.
Right, so it's the increase in temperature, good. Or you can think of it as, and this is a new term maybe, but the slope of the line, right? So the steeper that number is, or the higher that number is, the steeper the slope will be, right? So remember, here are our two graphs. The green one has the 21, this is the 2175, D plus 10, right? That's our temperature. And this one is 145, D plus 10. So that number dictates the steepness of that line, okay? And it also dictates the direction. That number, and we're going to see this later on, but if it's positive, it means the ramp's going up. If that number's negative, that means the ramp's going to go down. Okay? All right, so we know what that number is. And what does the 10 dictate? Matthew, in front of Max.
Sorry, what was it?
What is the 10? What does this 10 dictate on the graph?
Oh, the original degrees of the Earth's surface.
Yeah, so what do we call that point on the graph?
The starting point.
No? AJ?
The partial variation?
No? It's got actually a name. Yeah? Preston?
The fixed cost.
No. Henry?
So y-intercept.
Yes, good. Y-intercept, okay? You might not know that word yet, but it's the y-axis, right? And where the x value is 0, where it touches the y, that's called the y-intercept. Okay? So that's what that represents. So therefore, the 10 is the y-intercept. And this is the slope. We're going to learn more about what exactly the slope is and how to find it, as well as the y-intercept, okay? Moving on. The graph illustrates the total cost C in dollars of a taxi fare for distance D in kilometers. Kyle at the back. Can you read?
The fixed cost of Q represents the initial unit fare.
A little louder, Kyle.
Or is variable depending on the passenger's destination. For this reason, the variable cost is 50 cents times the distance. Do I continue?
Yep.
The graph is a straight line, but it does not show direct variation between the line. Does not pass, because the line does not pass through the origin. This type of relationship is called a partial variation. Another way to describe this partial variation is to say that C varies partially with D. In general, if Y varies partially with X, the equation is of the form Y equals mx plus B, where m and b are constants, and m represents the constant variation, b represents the fixed or initial value of Y.
Okay, good. So partial variation, it's a relationship between two variables in which the dependent variable is the sum of a constant number and a constant multiple of the independent variable. Okay, so the dependent variable, which we know is y, is equal to the sum, so the addition, of a constant times the dependent variable, x, plus another constant. All right, so this equation here, y equals mx plus b. Who's heard that before? Where'd you guys hear that? Grade 8?
Yeah.
Somewhere? Adam?
Yeah, grade 8, and my sisters.
Grade 8? You will see and hear about y equals mx plus b for the next 2 years, I'm going to guess 1,000 times. You're going to hear your teachers say that. Very important. In this class, at least a couple hundred times. Y equals mx plus b. It's one of those famous equations like the Pythagorean theorem, a squared plus b squared equals c squared. Y equals mx plus b is one of those type of equations that you will always hear about. Okay, so very important that we understand the parts of this equation. What it does is it relates the y values, those dependent values, with the x values, the independent values. Okay? The b value, I don't know why they call it b, but b is the y-intercept. Okay? So in other words, it's the value on the y-axis when x is 0. That's b. Okay? Why is that the case? Because if I sub in x is 0, anything times 0 is 0, so it would be m times 0 is 0, y is going to be equal to b. Okay? So when x is 0, the y-intercept value is b. All right? And m is called the slope, and that dictates how steep your line is. Also the direction. So positive goes like this. You read it always from left to right. Positive, if you're like that, your m value is going to be negative. Okay? Positive, negative, y-intercept is your b value. Okay? So in the last example then, b would be what in this taxi fare example? Steven?
Well, wasn't it 10 for the first one?
Yeah, 10 for the first one, but for the taxi fare?
$2?
Yeah, so b would be then what?
$2? 2?
2. Good, b is 2. Okay. Who can go ahead here and tell me what m is for this graph? Sal.
0.5.
How'd you get that?
Because starting at 2, every kilometer the cost goes up by 0.5. So
Excellent. Very good. Perfect. So what is the equation, Sal?
So it's going to be y equals 0.5 x plus 2.
Very good. That's a huge part of grade 9, what Sal just did right there. Believe it or not. Understanding what the slope was, the y-intercept. I know it seemed really easy, that's good, but that's a big part of grade 9, okay? If you don't understand what happened here and what he did, now's the time. We have to get it clarified, okay? Slope is huge, okay? That m value is huge. We're going to get a formula to how to calculate it in a minute. Adam.
I was just about to say, m is rise over run, right?
Yes, that's right. Yep. We'll explain it in a minute. It's the amount that the value rises over the amount that it runs. Okay, in other words, the y value difference over the x value. So here you can see the y value difference is 0.5 and the x value difference is 1. So it's 0.5 over 1. It's 0.5. Okay? We're going to have some time. We're going to get there. But that was good so far. All right, example 1. Graph of partial variation. Sebastian.
Copy and complete the table of values, given that y varies partially with x.
All right. So, can we complete this table? We know when x is 0, y is 6. So what's the value of b here then? What's b? Matthew in the front.
6.
Good. B is 6. Good. Excellent. Okay. And then we know when x goes to 1, y goes to 9. So if it goes to 2, what's y going to go to here? Matthew again.
12.
Excellent. We're going up by 3, right? And so then here when it goes to 4, it's going to go to Matthew?
18.
Good. And this is obviously good. Oh, sorry. They jumped to 27? Yes, thanks. So they jumped, how many values of 3 did they jump?
That's 7.
It is 7. Yeah, it is 7.
Thank you, yeah. That's strange, right? You'd never see a table that does this. You wouldn't just skip 3 values on the x. You wouldn't do that. They threw that in as a curveball. Okay, B. Identify the initial value of y and the constant of variation from the completed table. Write an equation relating to y and x. So we did the initial value of y. We said b is equal to 6. What about the constant of variation? So what do they say when they